Yeah, Nino, do you want to try sharing your screen?
Okay.
Yeah.
Yes, this seems to work. Yeah, this seems to work. Right? Can you see the screen share?
Yeah.
Okay. Good.
Okay, let's start.
Okay, so we just begin with my talk and then we. Okay. Let's turn the screen share. Okay. So thanks for inviting me to the seminar and giving me the opportunity to talk here. So let me start my talk with a little bit of an analogy. So assume that you want to take a hiking trip. So you're somewhere in the mountains, for example, and you want to take a trip. So you already know where you want to start your trip, and you already have some idea where you want to go. So you have the start and end point already in mind, and you have something with you like this, like a map of the terrain. And this map contains useful information. So it will give you all the information of the pathways that you might be able to take that would lead you from A to B. It gives you some information about the topography of the terrain, like the height difference that you might need to overcome. And it also gives you some information about the length of the pathways. And with all this information in place, you're then able to condense this, and given your preferences, you're able to decide, okay, which is like the best option for you to take, like which is the pathway that is best to your desired hiking route that you would like to take. So this means that, okay, in order to find the best according to your preferences hiking route, you need the information of the topography of the terrain. You need a collection of all the available trails. You need to find all the paths that can lead you from A to B. And you need also a way to rank these pathways according to your set boundary conditions. And that's basically all the information that is encoded in this hiking map that I showed. Now, where I want to go is the question if it's possible to do a similar thing for chemical reaction networks, okay? So assume, or like chemical reaction spaces in general. So assume that you have some chemistry in mind that you already want to study, and you're able to come up with a chemical reaction space, like a possibility space of all the reactions that are in principle viable given this chemistry that you want to study. Then a way to weight all these reaction edges with, for example, the energy differences in the edux and products, like the free energy, the reaction free energy, and a way to like find all the paths. So saying that you already have a set of educts and a set of products, then finding all the pathways, and then a way to rank these pathways accordingly. So basically, in order to find now the quote unquote best pathway according to your set boundary conditions in such a chemical reaction space, what you then need is basically a method to expand this chemical reaction space in the first place. So to find all the possible, like the reactions that are in principle possible. A method of finding all the free energies of the reactions. a way of finding all the viable pathways that lead from your given set of educts to your set of products. And then finally, again, a way to rank all these pathways. So such that you have a possibility to find what is like the most efficient or best pathway given to your boundary conditions again. And yes.
Nino, do you mind removing the thumbnails from the screen? Like,
Okay, yeah, okay. I'm never sure. This is always this annoying thing with Zoom. Okay, I'm never sure if there's black boxes there or not.
yeah, that worked. That
Yeah,
worked. Thank
sorry.
you.
Okay.
That's perfect.
Yeah, it might be a Linux problem. I don't know. Okay. Good. So I will touch on all these 4 points, but I will mostly focus on the last point. So I will talk a little bit about the first 3 things, but the main idea is that I want to talk about the last thing, like how can you rank pathways? So the methods that are going to be employed are that for a rule, so for expanding the chemical reactor space, you can do something that's called a rule-based expansion. Which you can do using the software package of Möll. So some people in the audience might already be familiar with Möll. I'm not going to go too much into details, but in principle, the main idea of Möll is that you define a so-called graph grammar, where you formalize your molecules as graphs and the reaction as graph rewrite rules. And then you can define a set of initial molecule graphs and a set of rewrite rules that you can then iteratively expand, again, given some set constraints to obtain an overall chemical reaction space. So this is basically then all the reactions that are in principle possible within this chemistry. And once you have such a chemical reaction space expanded, you can then retrieve its stoichiometric matrix, for example. So the matrix of all the stoichiometric coefficients from all the reactions that you find, which you can also further split and then in the educt and the product stoichiometric matrices that already contain some useful information that you can later then have. The search for autocatalytic cycles, so there are several ways of doing that. One very neat way of defining autocatalysis is a network topological definition of autocatalytic reactions, where you basically say that, okay, every autocatalytic reaction you can define as a reaction that has like a main cycle going on. But at some point you have like a split point, a split reaction that creates like a side branch. Sometimes is also called like a hyper-ear that at some point feeds back into the main reaction cycle. And this merge point is then basically the autocatalytic species. You can either try to search directly for such a motif inside a chemical reaction space with a very nice tool that was written by Philip Honecker, or you can already use the built-in functionality of Möll that is called the integer hyperflow query that allows you in general to search for pathways inside this chemical reaction hypergraph. And it also includes a way of finding pathways that are overall autocatalytic. A quick example of what these hyperflow queries are doing. So basically, you can get for a chemical reaction network then all the information of which reaction is firing and how often. And then this you can then condense into a flow vector V that then basically contains all this information, such that when you multiply this flow vector with the stoichiometric matrix, you get the net flow from this reaction pathways. Okay, so how do you now estimate like the cost of such a pathway? So how much it costs for a certain pathway to run?
Nino, sorry
Yes.
to bother you again, but now there is another thing at the top of your screen which says you are screen sharing. Yeah, can you move that? Just because it's covering your title.
Question. This is the that's the Zoom stuff.
Yeah. Yeah, hit the more. Hide video panel. It's the third last command when you hit the more. Yeah. Let's try that.
No, I don't see
that
the
didn't
other.
work. Can you move it around?
Hover your mouse around the green line and see what option it gives you.
No, there is nothing here. Weird. I mean, the titles are not.
Maybe just put it on the right.
Okay.
Yeah, exactly. That'll work. Yeah, it works now. Please continue.
You're muted, maybe.
I might have accidentally clicked mute when I moved that panel. Yeah. Okay. So back to the talk. So estimating the cost of such a reaction pathway. So basically, when we have any chemical reaction, we can define it, as the set of all the educt complexes that goes to all the product complexes. And assuming that all the reactions are reversible, then this means you have a forward reaction K plus K, that should say K minus, whatever. You have a forward and a backward reaction, backward rates for these reactions. Given this, you can define an equilibrium flux for each reaction. It's basically assuming that when you are in equilibrium, in a linear response regime, that basically you have like the fluxes of the half reactions from the forward and the backward reaction should be the same. And this gives you then this equilibrium flux. And when you have this,
sorry. So this equilibrium flux means reversible reaction balance, to say. So it's
yes.
So it's for all reactions. So it's let's say much stronger than equilibrium for differential equations style, which is just the derivatives of
it comes from you have to assume what's called mass action kinetics, right? These are basically from mass action kinetics, the fluxes of the forward and backward reactions, but with the when you are already at the equilibrium concentrations.
Yeah, but the equilibrium is here strong. Okay, yes.
Yeah, well, okay. I mean, sure. I mean, first of all, you have to assume also a closed system. Plus,
if I may say, it's what some people call detailed balance.
Exactly. Yes.
So in each reaction, you have forward equal backward flux, like you said.
Exactly. Yeah. So we have to. So you have to assume that detailed balance holds and that each reaction is in principle reversible. This does not mean that in practice some reactions might be in practice not really reversible because there's such a high forward rate that the backward reaction virtually is not happening. But for thermodynamic completeness, here you have to assume that the reaction is in principle reversible. Yes. Yeah. And also like this whole thing is basically an approximation that was done by Eric Smith in this. It's a bit of a very involved paper. And so, I mean, this is really just like a first approximation that only works when you assume that you're close to equilibrium in the linear response regime. In principle, you could generalize this, but yeah, this gets then a bit too involved. So I will stick to this linear response regime for now. And in this linear response regime, at equilibrium, you can then define the energy dissipation or the cost of such a flow pathway when you have the flow vector V, basically as it's basically the inner product of the vector with itself rescaled by this equilibrium flux. So it contains basically the length of the pathway that is rescaled by this equilibrium flux. And this basically tells you how much does it cost you to project such a pathway out of this equilibrium. Okay, so this means that in order to calculate this Q dot, we need to calculate we need to calculate the equilibrium flux, and for this we need the forward or the backward rate and the equilibrium concentrations. To get an estimate of the reaction rates, we can use thermodynamic properties. So when you have a reaction, we know that, okay, basically the energy of the reaction is just the difference between the reaction-free energy of the educts and the products. And depending on whether the reaction is endergonic or exergonic, like whether you're, it depends what says whether the delta G is positive or negative. So whether you go from a higher energy state of your educts to a lower energy state of the products or vice versa. And then in principle, you also have the energy barrier, like it's the kinetic barrier, which is like this activation energy that you usually have to overcome in order for a reaction to run. I will come to that again in a minute. But in principle, in general, you can get this reaction free energy delta G as the sum of all the product complexes times the corresponding stoichiometric coefficients minus the sum of the educt complexes, again, times the corresponding stoichiometric coefficients. So in order to calculate delta GR, you basically need the energies of formation of all your species that are involved in your reaction space. And this you can usually calculate using some software tools. So depending then on your delta G, so again, whether it's endergonic or exergonic or endergonic, you can then basically compute the reaction rates either as e to the minus the energy barrier over RT for the forward rate, or the energy barrier minus this energy difference over RT in the backward rate, or vice versa if it's endergonic. So basically, you just have to get, okay, which is like this hill that you have to overcome in order for this reaction to run. And in both cases, you can get your equilibrium constant as just dividing the forward over the backward rates, which is then basically just e to the minus delta, so delta G over RT. So this is a nice way that you can basically scale everything according to thermodynamics. So everything, if you define your reaction rates like that, this should be thermodynamically sound. And in your equilibrium constant, you then have all the necessary information, whether your reaction goes forward or backwards, predominantly the forward or the backward reaction. You still need to have some estimation for the energy barriers, but since estimating energy barriers is not always easy, you can make a first approximation by assuming perfect catalysis. So basically setting the energy barriers to 0. And in this simple approximation, then basically the forward rate then just becomes 1. So if you have a delta G smaller than 1, and then the backward rates is just 1 over the equilibrium constant, and it would be vice versa if the delta G is bigger than 0. And then this equilibrium flux is simplified to this equation here. So you get the energy barriers out of the equation. And it's again analogous if the delta G is bigger than 0. Okay, so this means that we basically, all we have to do then is we iteratively expand a chemical reaction space using a rule-based method in Möll, and get from there the stoichiometric matrix of this chemical reaction space. We can then use the built-in hyperflow query to obtain all the pathways within the given boundaries obtain the corresponding flow vectors. Then we can compute the free energies of formation of all the species within the chemical reaction space. As I just said, you can use software methods for that. For now, I've been using the Equilibrator software, which implements a group contribution method. You can also use quantum chemistry methods, but for the systems that have been studied so far, the Equilibrator with its group contribution method is sufficient. But it's also just a first approximation. And from the energies of formation, you can get the reaction-free energies as well as equilibrium constants. And then, assuming that you have some information of the initial concentration of your educts, and together with the stoichiometric matrix and the equilibrium constants, you can then compute the equilibrium concentration. This can be done again using a software package. I've used the Python package EQTK, which basically just solves an optimization problem for this boundary conditions. And then with all this information, you can get the equilibrium flux as well as the dissipated energy for each of the pathways. Okay, let's look at the simple case study. I chose the formos reaction, not because it's an interesting system, but because it's a very well-studied system that also has a very simple chemistry that's easy to approximate in this rule-based method. So the reaction system, so this classical formos reaction with this which is this Breslov cycle, takes formaldehyde and glycoaldehyde initially in the system that then continue to react through a series of keto-enol isomerization and aldol or retroaldol reactions to create a very simple autocatalytic cycle that where each turn of the cycle you get 2 copies of this initial glycoaldehyde out of it. So the reaction grammar therefore only involves 4 reactions. So 4 reaction rules. So for the keto-enol isomerization, you just define a reaction rule in the forward and in the backward reaction direction. And you define a reaction rule for the aldol or retroaldol reaction. So again, in the forward and backward direction. To avoid a combinatorial explosion that can easily happen in such a chemistry, you need to also define some constraints. For example, disallowing the possibility for weirdly branched side chains, because otherwise you might end up with a very dense chemical reaction space. And yeah, your initially present molecules are glycoaldehyde and formaldehyde. So doing constrained expansion with where you don't allow any molecules with more than 6 C atoms. Again, otherwise your expansion would never terminate. So you need to define a certain size cutoff. You end up with a chemical reaction space that contains 37 molecules in total and 100 reactions. And using the hyperflow query method of Möll, you can study the first 100 solutions that are autocatalytic with respect to glycoaldehyde. Okay, now comes the interesting thing, so ranking these pathways. So basically, for a first calculation of this pathway rank, so when you're calculating the energies of formation for all these 37 molecules, and then calculating for all these 100 reactions, the reaction energies and the equilibrium constant, and assuming as initially that you have a concentration of 1 millimolar each of formaldehyde and glycoaldehyde, then putting this into this Python package to get the equilibrium concentration, and then calculating the equilibrium flux and the dissipation, you get this curve. So on the x-axis is just the index of each flow solution. It's basically the order in which the software package finds them. So not necessarily any specific orders, just like, okay, if it's the first, the second, the third, until the 100th solution. And on the y-axis, you have this dissipation that was calculated. And the blue dots here represents the classical Breslov cycle. And you can already see that while it's that one of the autocatalytic pathways that is found with a low dissipation is not the lowest. So there are some pathways that you can find that have a lower dissipation. And now you can start tweaking around parameters. Now you can see, okay, how does this do these pathway dissipations change when you change some parameters? For example, how does it change with the initial concentration? So you can go to another extreme by assuming that you start with no formaldehyde at all, and just glycoaldehyde, you still get an equilibrium distribution. That's because since the network you get is very dense, it is in principle possible that you find reaction pathways that lead from glycoaldehyde to all the other molecules, and therefore you will find an equilibrium concentration. This would, for example, not work with only formaldehyde. So, but glycoaldehyde, it can react with itself to form big, longer chains from which then formaldehyde can branch away. So this works fine. But the overall dissipation from the pathways is higher. So since you now are in a lower concentration regime, it costs you more to project each of these pathways out of the equilibrium.
Excuse me, may I ask a stupid question?
Yeah, sure.
What we are seeing here is the energy it takes to run the reaction 40, for example.
Yes.
Is that
yeah.
Or the net energy or something? Is that what we are, just the graph that we are seeing here for different parameters?
Yeah. Well, in principle, it's more like, okay, how much does it, like the cost to project this subgraph that is represented by this pathway out of equilibrium.
So
in principle,
the vertical,
this dissipation should be, yeah.
The vertical axis has a very cryptic identification. It's, if I read correctly, it's Q dot prime I. So can you remind me what is Q dot prime I?
Yeah, so okay.
What are we seeing here?
Yeah, right. So the Q dot is this dissipation that is calculated. Where was the formula? No, here. And it's basically the inner, so you're calculating like the length. So the V are the path, the vector that is representing your pathway. So this gives you the information of like which reaction is running.
Okay.
Which reaction is running and how often.
It's a 1-0 vector. Okay.
Not necessarily 1-0, but like 0 or like 1 or 2. So it can also contain reactions that have to operate twice in order to realize this pathway.
Okay. Yeah. Thank you very much.
Yeah. Okay. But just to, so it then basically this Q dot is then something like the length of this pathway that is then rescaled by this equilibrium flux. It should have no unit, so it should be really just how do you say, like some cost estimation. Yeah. And actually, so it's just about, and there's actually the prime. So by like really like when I calculated these things, this Q dot came out quite big. So I just rescaled it. So it came out as something like 10 to the 7. And I just rescaled everything by a factor 10 to the 7, because it's not so much the question of how high the Q dot is, but like how they are relative to each other. So which is the pathway with the smallest Q dot? As much, I mean, I have to admit at this point that this is all from this paper from Eric Smith. And the paper is very involved, and I have to admit that I don't understand everything 100%, but that's at least how I understood it so far, and how how this was also like in discussions with Profil, for example, when he visited our group. So
and this is a snapshot for one particular choice of little v.
So the x-axis is these, yeah.
Yeah, exactly. On the x-axis, you have all the flow vectors.
Exactly.
Yes. But yeah, good question. So for example, this blue dot is then like the flow vector that corresponds to the classical Breslov cycle, which is this one. So for each of these flow solutions, you then can get this dissipated energy, this energy dissipation, or like this dissipation relation. And yeah, changing some parameters then also changes in general this dissipation. So they get higher relative to each other. That's the whole point.
So horizontally, we see one particular choice of path. Is that correct?
Not all the pathways that you get. So you get 100 flow solutions. So yeah.
Pathways, yeah.
Yes.
So this is about 100 paths. Thank you very
Yes.
much. Yeah.
Actually, so this is also like a good transition for me to my next slide, because since the x-axis doesn't really matter, you can order it.
Yeah.
So the x-axis really contains the information like, okay, that's the first pathway we found, that's the second pathway we found. So we can take the blue and the red curve and just order them by the y-axis, which then results in this curve. So now the x-axis you can really ignore. It's really like, okay, I took all the information from the previous figure, from the blue curve and the red curve, and I just ordered them according to this q dot prime. So now basically on the lower end, you will get for the choices of parameters that result in the blue curve, the path with the least dissipated flux, and on the right side, the path with the highest dissipated flux. And the same as for the red curve. So the order, actually you can ignore now the x-axis because they don't even have to be the same indices. So here they were the same indices. So in this curve, this was like the 10th that you found for the initial concentrations of 1 millimole each of formaldehyde and glycoaldehyde. And then the same flow solution, but with lower concentration. But now it's really like, okay, you just order them according to the dissipated flux. Yeah. And what's interesting now is that, so the red curve is still above the blue curve, but the location of the Breslov cycle shifted. So relative to all the, so in the blue curve, relative to all the flow solutions that you get, the solution that corresponds to the Breslov cycle lies in the lower regime, but it's not one of the best. But in the red curve, which is a lower concentration regime, the Breslov cycle gets better. So we're still worse in comparison to the blue curve, but better to all the other flow solution that you get for the thermochemical landscape that results in the red curve. And that might be an interesting result here, because according to the literature, the Breslov cycle usually seems to be running better in a low concentration regime. Okay, so finally we can compare this, for example, what is like the most optimal, like the pathway that has the least dissipation, which is, by the way, the same in both the red and the blue curve. And compared with the classical Breslov cycle. So here you find a Petri net representation of the classical Breslov cycle, which takes two formaldehyde and a series of isomerization reactions through keto-enol isomerizations. And then you split off, so you end up in this tetralose sugar that then splits into two glycoaldehyde. And this minimal dissipation pathways runs in a similar fashion until this tetralose, but then it binds another formaldehyde that then asymmetrically splits into glycoaldehyde and this glyceraldehyde dihydroxyacetone, sorry, which then isomerizes again and splits off one formaldehyde and again a glycoaldehyde. So it follows basically the same reaction backwards that it did. So the first part of this reaction path and the last part is basically the same. It's just that they are going in opposite directions. I found it interesting. But yeah, okay. So to wrap things up, basically what we now have is a nice way to study chemical reaction spaces. So I showed here the formalized reaction, but in future I would definitely also try to apply this same method to other types of chemistries. Yeah, so The zero barrier approximation is a valid first approximation, but yeah, for studying more realistic settings, one should definitely try to introduce the kinetic barriers back into the equations and try to get an estimation of equilibrium fluxes that includes kinetic barriers. And in generally also move away from this whole near equilibrium approximation. And yeah, then basically also what effects the change of parameters have on this path dissipation. So not just changing the concentration, but also what might change if you, so some of the reactions might be sensible to pH change that then might change the reaction rates, and this will definitely also change this dissipation value. Yeah, and then in principle, this should all lead to answering the question that, okay, once you have a certain chemical reaction space in place, to find out how specific pathways could emerge out of this chemical reaction space. And yeah, that was more or less it. Thank you for your attention, and also thank you again for inviting me to the seminar.
Thank you so much, Nino. It was